Hi everyone, this is Dr. D. Nagaraju, Assistant Professor in Physics, Department of Basic Sciences, School of Sciences and Humanities, SR University, Warangal. My presentation title is Semiconductors for Beginners. Why we need to study these semiconductors? Because they are the heart of modern technologies. Semiconductors are used to make diodes, transistors, integrated circuits, solar cells, LEDs, and computer chips. Without semiconductors, there would be no smartphones, laptops, or no internet. Semiconductor materials are used to make devices that consume very low power and work very effectively. Technologies like 5G, medical imaging, and smart sensors are powered by different types of these semiconductor components. Classification of materials by conductivity. What is conductivity? How we can define this conductivity? Conductivity is the ability of a material to allow the flow of electric current through it. That means the conductivity of a material is completely based on the availability of free charge carriers. Based on this, materials are classified into three types: conductors, insulators, and semiconductors. So conductors means it has a high conductivity. Examples are copper and silver. That means if you take a conductor or if you take a copper or silver material, where we can see more number of free charge carriers in that material. If you have a more number of free charge carriers, then where we can see a more conductivity. Then coming to insulators, it has a very low conductivity, but means to say that there are no free charge carriers to allow the current through it. Examples are glass and rubber. So coming to semiconductors, in a semiconductors, where we can see uh, a medium range of conductivity, that is intermediate conductivity, we can see in the semiconductors. Examples are silicon and germanium. So in the classification, we have semiconductors and conductors. Already conductors have a good conductivity, then why again we need to use semiconductors, and why we are using these semiconductors in the modern technology? If we take conductors, a conductor has a more number of free charge carriers. If we apply a potential difference on this conductor, the free charge carriers will move in one particular direction based on the applied voltage. If there is no potential difference, then there is no flow of charge carriers in the conductor, but they will move randomly, but it will not generate the current in the conductor. That means if you provide a potential difference, we can see the current. If there is no potential difference, then there is no current in that conductors. That means fixed high conductivity will generate in the conductors. If you take semiconductors. In this semiconductor, there are free charge carriers are there, but limited number of free charge carriers will be there, depending on the applied voltage and depending on the fabrication of the semiconductors, where we can control the flow of charge carriers. Here, there is no effective control system on the conductors, but here, based on the fabrication, based on the applied voltage, a semiconductor can act like a conductor, and a semiconductor can act like a insulator also. Semiconductors, it will not amplify the signal, where the semiconductors, it can perform amplification, the switching process. Like you can see here, these are the examples of wire, electrical circuit, power transmissions. We can see in the conductors. In case of semiconductors, these are the enabled active devices, transistor, diodes, LEDs, and the solar cells. So far, we have been discussing about the availability of free charge carriers in conductors and semiconductors. But it is very important to know the how we can generate free charge carriers in a semiconductors. To know the generation process of charge carriers, it is important to study, but it is important to know origin of energy bands of a system, of a material. Now you can see here, I have here one individual atom is there. Atom consists of a nucleus at the center. You can see here, this is a nucleus, and around this there are some specific allowed atomic energy levels are there. This is the one is atomic orbital, where we can see two allowed electrons, and here this is one 2s atomic orbital, where we can see two allowed electrons, and here this is a 2p atomic energy level, atomic orbital. In that case, we can see here 6 electrons are occupied here. Now, each and individual electron will generate a separate energy state. Now, here what I'm doing here, here I'm taking here I'm taking a coordinate system, or x-axis, and this is the y-axis, and y-axis I'm taking energy state of an individual atom, individual electron. Now you have in case of 1s atomic orbital, where we have two electrons are there now. Now in for first electron, it will occupy one energy state. That means two electrons are there, the same 1s state, 1s atomic orbital. Therefore, these two electrons will occupy at 1s atomic orbital energy state. Okay, this is a discrete, we can say here a discrete energy level of or the state of the system. Now you can see here 2s atomic orbital, again two electrons are there. So for these two electrons, they will occupy a different atomic energy levels. And here six individual electrons are there in a 2p atomic orbital, and these 6 electrons will occupy here this 2p energy state of the system. Now, all these individual energy states are called discrete states of the system. This is about a complete energy system regarding a single atom. Now, if you want if you want to know the crystalline material, so crystalline material means where we can see here, in this case we have only as individual atom is there, but here I'm taking a crystalline material. But because here whatever the germanium and silicon materials are there, those are semiconductors, and those semiconductors are a crystalline materials. Crystalline materials means they have a perfect periodic arrangement. Okay, so now you can see here, let us assume that here one periodic arrangement of atoms. So each and individual atom behavior is similar to this one. Now you can see here 1s atomic orbital, here 2s 2p, here also 1s 2s 2p atomic orbitals, all they have individual atomic orbitals. If these individual atoms are in a crystalline material, now these atomic orbitals will overlap with each other. Then after it will generate the molecular orbitals. So now those molecular orbitals, the generated molecular orbital energy levels, we can see here. This is 1s molecular orbital energy levels of all the atoms which are there in the crystalline materials here. Now you can see here, in this case individual atom where we can see only one as a single energy state is there. But here whatever the 1s atomic orbitals are there in the entire crystalline materials, they will overlap and will generate the energy levels, and those energy levels will form a energy state here, will form a energy states. So now this is about the state of 1s of all these atoms. Now we can see here, this is a 2s atomic energy states of the atoms which are there in the crystalline materials. Similarly you can see here 2p also. So now you can see here all these are the energy levels, and those energy levels are combined together here. That means here 1 is combined and 2 is combined and 2p combined. So these energy levels are called energy bands. You can see this is one energy band, and this is 2p energy band, this is 2s energy band, and this is 1s energy band. Now we have a clear idea regarding the energy band formation in a crystalline material. Then now we are going to discuss about the band formation in a semiconductor material. In here I'm taking a semiconductor material, silicon atom. Now here the in a silicon atom electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p. Now here whatever the 1s2, 2s2, 2p6 are there, all these energy states are completely filled. All these atomic energy states. This is a first atomic orbital. It is completely filled with an electrons, and here 2s2, 2p6. It is also completely filled with electrons, 8 electrons here. But here, whatever the outermost orbital is there for a silicon atom, for a silicon individual atom, only 4 electrons are occupied here. Only 4 electrons are occupied. Now, if this silicon atom exists in a crystalline material, that means if you take in a crystalline material of a silicon, so now these are 3s2, 3p2 electrons, individual atomic energy levels will overlap with the neighbor silicon atoms in a crystalline material. With that, what happened? Due to that overlap, it will form the energy states. It will that overlap will generate the individual energy states, and those energy states will form a band here. Okay, now this a band a band is nothing but a collection of energy states, allowed electronic energy states. This is called valency band. And whatever the empty energy states are there, empty electronic energy states are there, those empty electronic energy states with the overlap in a crystalline material will form a conduction band. So now a conduction band, a band, it consists of a set of energy levels, a set of allowed electronic energy states here. At room temperature, at absolute room temperature, all the filled electron states, completely filled electronic states will available in the valence band. And whatever the conduction band is there, all these energy levels are completely free. No single electrons are there in this conduction band. So now here a band, your band is nothing but a collection of energy state here. So now in case of germanium and silicon, there exists a separation in between valence band and conduction band. If we talk about the conductors, we can't see such a band gap, energy band gap in between the conduction and valency energy band. So we can see some energy gap between conduction and valency band in semiconductors only. Now that energy band gap, energy gap, that means we can define here energy gap. This is a conduction band. Now here actually all these are the individual and allowed energy states, and we can see here all these are the discrete, but those discrete energy states are very closely packed energy states. So that's why we are writing it as a band, conduction band here. And here this also says the same. Now all the energy levels here, the individual energy levels here, all these energy levels are closely packed, and those energy levels will form a band here, that is a valence band. Now you can see here we have to define an energy gap here. The energy gap is nothing but the lowest energy level of the conduction band. It can be treated as a EC, and here the highest occupied energy state in the valency band is EV. Now this separation, the separation from between this EC and EV can be written as a energy gap, that is EG is equal to EC minus EV. So this is what the definition of energy gap. Based on the materials, based on the crystalline materials of semiconductors, the energy gap will change from material to material. And one more thing is, only whatever the energy state is there here, on this particular energy state, only two electrons can occupy. So that is what the a single energy state in a conduction band or a valence band. In the previous slide, we have classified the materials based on the conductivity, like conductors, insulators, and semiconductors. Now, I am doing the same classification, but based on the energy gap. Energy gap means a gap between conduction and valence band. Now you can see here, in case of conductors, the gap between conduction and valency is almost zero. That means we can see in materials, in the case of conductors, we can see overlap of conduction band and valency band. That means it generate the current, or in order to provide a conductivity in a conductor. Actually, electrons, the valence electrons, valence electrons, whatever the valence electrons there in the valence band, they have to move into the conduction band. Then only we will get the conductivity or the current. Now here there is a complete overlap. With this, what happened? Easily, the free charge carriers will move from valence band to a conduction band. Now here you can see insulators. The gap between conduction and valency is very higher. It's almost equal to 3 electron volts. It means we have to provide a much more amount of energy to move a valence electrons into the conduction band. So this is very difficult to get the conductivity in insulators. Whereas if we take a semiconductor where we have a good advantage, the gap between these two is in a considerable quantity. In a considerable quantity we have. That is, energy gap is almost, it should be less than 3 electron volt. For example, if we take a semiconductor silicon, where we can see the energy gap is 1.1 electron volt. For germanium, it will be 0.7 electron volt. So that means, uh, depending on the applied voltage, we can able to allow the free charge carriers, or we can able to move the free charge carriers in the semiconductors. So this is what the classification based on the energy gap. Now, these semiconductors are classified into two types. Then why we need a classification here? Why? Because if we take pure semiconductors, the free charge carriers, the number of free charge carriers in the valence band and conduction band are equal. But to improve the conductivity in a semiconductor material, we need a more number of charge concentration either in the conduction band nor in the valence band. So then what we have to do in that such case? So then for this generation of free charge carriers in a semiconductor, we have to add impurities. We have to add impurities to this pure semiconductors. So now, based on the impurities, adding impurities, semiconductors are classified into two types. One is a pure semiconductor, where we can see equal number of charge carriers in valency band and conduction band. But next one is impure semiconductor. Now what we are doing, we are adding impurities to the pure semiconductor material like germanium and silicon. Then why we are doing here, why we are adding impurities? Why? Because I want to generate a free charge carriers either in conduction band or valency band. So now again this impure semiconductor or eccentric semiconductor classified into two types based on the type of impurity also. So now here what we are doing, this is the classification regarding whether you are adding impurity or not. If there is no impurity, then we can say intrinsic semiconductor. If we add an impurities to pure intrinsic semiconductor, pure semiconductor, then it comes under eccentric semiconductors. Now again, this eccentric semiconductors classified into two types based on the type of impurity. Now, if we add a pentavalent impurity, pentavalent means in outermost orbital where we can see 5 valency electrons. If we add such pentavalent impurities to the pure semiconductor material, so that type of semiconductor material is called N-type material. N-type material. So now what are the pentavalent impurities? Phosphorus, arsenic, antimony, etc. are the examples for pentavalent impurity. Then next one is for these pure semiconductor material, now I am adding trivalent impurities. Trivalent impurities, our examples are gallium, boron, aluminum, like these are the examples here. Now this type of impurity can be treated as a p-type semiconductor material. This is very important here. So adding impurities, pentavalent impurity, the semiconductor material will behave like a n-type. Now you are adding trivalent impurity, now that semiconductor behaves like a p-type material. So now pentavalent impurity can be treated as a donor impurity, and trivalent impurity acceptor impurity. Yeah, we can. So now you can see here, in case of intrinsic semiconductor, outermost in outermost orbital where we can see 4 valence electrons are there. 4 valence electrons are there. For this pure semiconductor, for this pure semiconductor, in order to get the stable state for this pure semiconductor, it requires only 4 electrons. Instead of that, what we are doing here, we are adding pentavalent impurity and trivalent impurity. With this, we can get different types of semiconductors. So in intrinsic semiconductors, here I'm taking a silicon atom. The silicon atom electronic configuration already we know about 1s2, 2s2, 2p6, 3s2, 3p2. Now here 1s2 is a completely filled atomic orbital, and 2s2, 2p6 is also completely filled atomic orbital. Now whatever the third atomic orbital is there, it is partially filled here. Okay, it is partially filled. Now, in order to get the stable state of an atom, it requires, now this silicon atom requires 4 more electrons. So now that means here the silicon atom is ready to accept 4 electrons here. But getting 4 electrons from the another atom, it is very difficult. We can't get 4 free electrons from another atom here. So now in that case, this silicon atom will participate in the covalent bond. That means the sharing of an electron. With that, what happened? That a silicon atom will get the a stable state. So whatever the atoms are there in a periodic table, all the atoms want to get a stable state here. So that means they want to get a completely filled atomic orbitals in the outermost orbital. Now here the silicon requirement is four it needs a 4 free electrons to get the stable state here. Now I am taking here a silicon crystal here. This is a pure silicon crystal. Okay. Now the silicon atoms are there in the lattice site. All these are the periodic lattice sites here. 1, 2, 3, 4, 5, 6, 7, 8, 9. All these are the lattice sites. That means now these silicons are occupied in the lattice sites. Now here I am concentrating center one here. The center one here. Now you can see here around this silicon atom, we can see here 4 dots are there. 4 dots means 4 valency electrons in the outermost orbital. Now this silicon atom wants to get a stable state. So now this for this silicon atom it requires 4 more electrons. So 4 more electrons. With that, what happened? This silicon atom will participate in the covalent bond process here. Now you can see here. Now this atom, single atom, is participating with the another electron of a silicon atom. Now we can see here one covalent bond is formed here. Now these 2 electrons are shared by these 2 single silicon atoms here. Now here one more electron is there. Now here this electron is covalently bonded with the another silicon atom here. Now these 2 electrons are shared by these 2 atoms here. Now similarly these 2 atoms are sharing here, and these 2 atoms are sharing these 2 electrons. Now with this, whatever the center silicon atom is there, now it has completely filled atomic orbitals. Like you can see here, completely filled atomic orbitals. I can see here 4, here 2, here 2, here 2, here 2. 8 electrons are there. Now in outermost orbital, it is completely filled. Now it is in a stable state. It is in a stable state. That means at absolute 0 Kelvin temperature, at absolute 0 Kelvin temperature, this is the crystal state of the silicon. If we provide a temperature greater than the 0 Kelvin, above the 0 Kelvin, with this what happened? Whatever the electrons are bonded in covalently, those electrons will break the covalent bond and will get the free charge carriers. That means here, if you provide a sufficient energy to break this covalent bond, what happened? This electron will will move from that place. That means here the dotted electron will move from that point. This is what happened. You will get the free electron. But now it is not bonded with another electron. Now it is a free electron. So now this free electron, this is what here you can see here. This is a free electron, and the missing state of an electron in the covalent bond, it can act as a positive charge. That means it requires one more electron. Already, actually, in a covalent bond, we have two electrons are there, but one electron is liberated due to the temperature, due to the temperature greater than the 0 Kelvin. This is what happened. That electron is liberated from this covalent bond where we get the free electron, but whatever the missing electron site is there, that electron site can act as a positive charge. Why it is positive charge? It needs a electron. It needs an electron that can be treated as a positive charge. Now that missing state of an electron in the covalent bond can be treated as a hole. Hole is nothing but a positive charge. And whatever the electron is liberated, that is an electron. Now with this, what happened? Above uh, T greater than 0 Kelvin temperature, now we have generated charge carriers. One is electron and another one is hole. Both are in equal number. It means whatever the liberated electron is there, this electron will jump into the conduction band, and the whole missing electron site will create a hole in the valency band. So that means this will generate equal number of charge carriers. Like this, for example, this is what we have discussed about a single covalent bond. If we take another covalent bond, then it will generate one free electron and one hole. If you take one more covalent bond, again it will generate one electron and one hole. Like this, it is a process in a crystalline material above the 0 Kelvin temperature. Now it is generating equal number of free charge carriers. Now here we can see here, this is the crystalline material. All the silicon atoms are there in a crystalline periodic manner. You can see here these are the valence band and this is a conduction band. So below the 0 Kelvin temperature, all these electrons are occupied initially in the valence band. Okay, now whatever the black color dots are there, all these are the electrons occupied in the valence band. If we provide a temperature above the 0 Kelvin, so whatever the electrons are there in the valency band, those electrons will jump from valency band or will move from valency band to conduction band here. You can see here three electrons are missing here, and these three electrons are there in the conduction band. Now here also three electrons are there actually initially above the 0 Kelvin temperature. Now they are occupied in the conduction band. So that means above 0 Kelvin temperature, now equal number of charge carriers are there. With this, there is no particular use. We have to create more number of charge carriers either in the conduction band or in the valence band. So for this one, then what we have to do, we have to add impurities here. So we had to add impurities to the pure semiconductors. That's why here, in case of pure semiconductors, minimal free charge carriers, low conductivity. Now what I am doing here, now adding impurities. Now with this, what happened? It will generate electrons in the conduction band. That means it may generate, by adding impurities, it may generate electrons in the conduction band or it may generate holes in the valency band. With this, what happened? We get the more free charge carriers, and we can increase the conductivity of the material here. Now, adding impurities to the pure semiconductor material, it is a very difficult process here. Uh, there are different methods are there to add such impurities in a pure semiconductor material. So among those, we have to know the substitutional impurity here. What do you mean by the substitutional impurity? So foreign atoms occupying the sites of host atoms. Now, what is a foreign atom and what is a host atom? We had to get a clear idea on this crystal. So now here I'm taking one a crystal. All those crystals in this crystal, all the atoms are arranged in a periodic manner. Now here we have two different atoms are there. Here blue color and yellow color. Two different atoms are there. Here now you can see here host atom is your blue color. All these blue and yellow color atoms are the host atoms here. Okay. So now what I'm doing here, I want to add impurities here. But in case of silicon, whatever the host atoms are there, all those host atoms are same, the silicon atoms only. Here the color is different, but we had to uh, think that whatever the atoms are there here, all these atoms are silicon atoms. So what I'm doing here, I want to add an impurity. So if we add impurity, we have to concentrate the size of the impurity atom also. Okay, so now already we have discussed we have to add two types of impurities. Okay, one is pentavalent impurity and another one is trivalent impurity. Then why pentavalent and why trivalent only? Why? Because already silicon requires four electrons. Why? Because in silicon outermost orbital only four electrons are there. Again, it needs four more free electrons to get the stable state. Now, instead of that, what we are doing? We are adding pentavalent impurities. But silicon requires only four electrons, but we are adding with the pentavalent impurity. That means the 5 valence electron atom we are adding to the impurities. That means now the foreign atom is nothing but a pentavalent impurity. Foreign atom is here what? A pentavalent impurity. If we add this pentavalent impurity, then it will create a impure semiconductor material, that is N-type. Then the second case, now what I'm doing here, I'm adding trivalent impurity. Again, our requirement is 4 electrons, but we are adding trivalent impurity. But means only 3 valence electrons are there. 3 valence electrons are there in that such atom. Now we are adding that atom to the silicon crystal. Now this trivalent impurity can act as a foreign atom. Okay, this atom can act as a foreign atom and host atoms are silicon. Now here one electron is missing here, and here extra one electron is there in a n-type material. So this type of adding trivalent impurities can be treated as a p-type material, and adding pentavalent impurity can be treated as a n-type material. Now here we can say here doped with donor and doped with acceptor. We can discuss this in the later slides. Now you can see here we have a periodic table here. This is pure germanium and silicon atom. Now if you have 14 and 32, now what we are doing here, fifth group element, fifth group atoms we are adding here. Now your arsenic, phosphorus, we are adding pentavalent impurities to this silicon atom. Then we can get the N-type semiconductor material. So what happened? If we add pentavalent impurities, what happened to the crystal size? Now you can see here, this is N-type semiconductor material. Now silicon atoms are there actually. All these are the silicon atom. All these are the host atoms. Now one host atom is substituted by arsenic. Okay, before adding arsenic, here we have silicon atom is there. For silicon atom, it has only 4 electrons are there. 4 electrons are covalently bonded with the other 4 silicon atoms. Now this is the case. But here, after adding silicon, after adding arsenic atom, arsenic has 5 valency electrons are there. Why? Because it is a fifth group element now, fifth group element in outermost orbital. 5 valency electrons are there. So among those, 4 electrons are covalently bonded with the silicon, like this here, like this here. Here this is one, and here also, here also, here also. 4 valency electrons of arsenic atom are covalently bonded with the silicon atom. Now extra one electron is there here. One unpaired electron is there here. It is unpaired. So now what happened? If it is unpaired, then what happened? It will move in the crystalline material. It has no particular bonding here. There is no particular bonding for this electron. So what happened? This excess electron will jump into the conduction band. It will move into the conduction band above the 0 Kelvin temperature. Now, so what I'm doing here I'm adding only single arsenic atom. For example, here for this crystalline material, I'm adding only one arsenic atom. And that's in such case, what happened here? You can get one electron in the conduction band. One electron in the conduction band. Now what happened, according to the previous case, if we take an intrinsic semiconductor above the 0 Kelvin temperature, what happened, some covalent bonds may break. With that, what happened, some electrons, equal number of charge carriers will exist in the conduction band and equal number of holes will exist in the valency band also. So with this, what happened, we have increased the charge concentration, electron concentration in the conduction band by adding pentavalent impurities. So if we add this pentavalent impurity in a sufficient manner, in a particular measurable size, so with this what happened? More number of free charge carriers will generate here. Excess free electron will enter into the conduction band. Will enter into the conduction band. Now, in N-type semiconductor material, now more number of free charge carriers are, the majority charge carriers are electrons. Majority charge carriers are electrons, and those electrons will occupy in the conduction band. So electrons are negative type. So therefore here conductivity based on these electron charge carriers. That's why you can see here N-type semiconductor. This is what N-type semiconductor material. So in such a case, we can say that here arsenic is a donor atom. What is this here? It is ready to donate an electron. It is ready to donate an electron. If any atom, if you take NaCl, sodium chloride, in the case of sodium chloride, sodium is ready to donate one electron. In such case, what happens? Sodium will get positive. It will become positive ion, and the chlorine will negative ion. So with this, what happened here, arsenic is ready to donate one electron. In such case, now this can be treated as arsenic is called a donor atom. It is called a donor atom. So this is what the n-type semiconductor material. Then the next second one is p-type semiconductor. Now slowly we are increasing the charge carrier concentrations in the conduction band and valency band. Now here, please here, if we add pentavalent impurities, we have increased the charge carriers in the conduction band in n-type material. Now I'm taking the same again silicon or a germanium semiconductor, pure semiconductor material. For this silicon or a germanium semiconductor material, I'm adding now trivalent impurity like aluminum and gallium. Then what happened if we add a trivalent impurity? Our requirement is 4 electrons, but we are adding uh, trivalent impurities to silicon atom. With this, it it may not be stable. No? So now let us see what happened here. Now here you can see here all these are the regular silicon atoms are there. Now all these are the host atoms. Now one host atom is replaced with the boron, but boron has only 3 valency electrons are there in the outermost orbital. 1, 2, 3. These 3 valency electrons are covalently bonded with the 3 more silicon atoms here. 1, 2, 3. So what about this silicon atom here? Please here boron is ready to accept 1 electron here. Now here actually in order to get a covalent bond it requires 1 more electron here. But no such free electrons are there in this. No free electrons are there. But it is completely empty. So now what happened that the boron requires here this covalent bond requires 1 free electron. It is ready to accept an electron. So that is a this can be treated as a missing an electron. The missing state of an electron already we have discussed. The missing state of an electron can be treated as a hole. Now here we here boron or this covalent bond requires 1 electron. So now this requirement of an electron can be treated as a hole and that is a positive charge. It can act like a positive charge here. Now where it will occupy here? At above 0 degree Kelvin temperature, whatever the missing state of an electron, that energy state will occupy here in the valence band. In the valence band. So now this is the state here. If we add a trivalent impurity, now here boron is creating 1 hole in the valency band. If we add such boron atoms, more number of boron atoms to silicon atom, what happened? More number of free charge carriers will also generate. In addition to that, some covalent bonds in between the silicon will also generate equal number of charge carriers. With that, what happened? So now the charge concentration in the valence band, whole uh, charge concentration increases in the valence band than the conduction band. Conduction band where we can see limited number of electrons will be there, but we can see here more number of free charge carriers will be there. Majority charge carriers will be there in the valence band as a whole. Now this is boron is called here acceptor. It is ready to accept an electron. So now this will act as a positive charge. So now this we are naming it as p-type semiconductor material. Broadly, we can say that in p-type semiconductor material, majority charge carriers are p holes, and in case of n-type semiconductor material, majority charge carriers are electrons. Now here we have to define Fermi level in semiconductors. Here the Fermi level in a semiconductor is nothing but it is the highest occupied electronic energy level at absolute zero Kelvin temperature. That is called a Fermi level. Now here if we take a intrinsic semiconductor, so now this is the highest occupied energy state of an electron, but it is not a physical existed energy state for this semiconductor or any semiconductor material. So now here we can see this is highest occupied energy state will get in between the conduction and valency band. In such case, we can write EF is equal to EC plus EV by 2. That means the lower energy level of a conduction band, a higher energy level of the valency band by 2 will get the Fermi energy level. It is exactly middle. Now if we take a p-type material, the highest occupied energy state of an electron is closer to valency band. It is very closer to valency band. In such case, you can write here this is where you can see here EF is equal to EA is acceptor energy level. So between the boron is ready to accept one electron, and now that will create a hole, and it has an energy state. So now that energy state can be written as a EA, and EV is the valency band energy state. That means highest energy level of the valency band. So with this, these two energies, the sum of these two energies by 2 will create a Fermi energy level. Now this dotted line will indicate the highest occupied energy state. Similarly, here in case of n-type semiconductor, the highest occupied energy state is very closer to conduction band. It is the case at 0 degree Kelvin temperature. Above this, for example, if we want to talk about above t greater than 0, what happened here? These electrons will enter into the valency band, and these holes will enter into the valency band, and these electrons will enter into the conduction band. This is the case at T is equal to 0 Kelvin temperature. Now this is what broad classification in between intrinsic semiconductors and extrinsic semiconductors, means pure and impure semiconductors. So already we have been discussing about all these things here. Semiconductor is a pure, and this is a impure semiconductor. And here charge carriers are produced only due to thermal agitation. That means we have to provide a thermal energy, then only you will get the charge carriers. But here in case of semiconductors, we need not to provide, but due to the pentavalent and trivalent impurities. Additionally, we get the charge carriers in the conduction and valency band. Here, where we can see a low electrical conductivity, here we can see high electric conductivity. Why? Because already we have discussed now, if we increase the charge carriers, then automatically conductivity also increases. Here low, and here high conductivity can get. These intrinsic semiconductors operate effectively in a low temperature, and it will operate at a high temperature. And we have know about in Fermi, and we know about at 0 Kelvin temperature, it is exactly middle. And in case of the Fermi level is p-type material, it is closer to valency band. In case of n-type material, it is very closer to conduction band. Now this is a difference between p-type semiconductor material and n-type semiconductor material. So this is what clear classification regarding how we get p-type semiconductor material. So simply trivalent impurities we have to add here to get n-type semiconductor material. Then we have to add a pentavalent impurity. Here impurity is called accept or impurity. Why? Because it is ready to accept an electron. Boron is ready to accept an electron. So that's why we can say it is acceptor impurity. Boron is an acceptor impurity. Here, in case of N-type semiconductor, the impurity is called a donor impurity. Means arsenic is then arsenic is ready to donate one electron. Okay, it has an excess electron. So that's why we can say that it is a donor impurity. So holes act as a majority charge carriers. Here, the electrons act as a majority charge carriers. Conductivity is mainly due to holes which are positively charged. Here the conductivity is due to only by the electrons. So this is what the classification regarding p-type and n-type material. So with this, and this is what about the semiconductors for beginners. Thank you for watching this video.